So let's go ahead and get started. So today I want to continue with our discussion of the Feynman rules for computing expectation values in quantum field theory. So just to remind you of where we left off last class, what we were interested in doing is computing the natural observables, that is to say the expectation values, in a quantum field theory. And so far we're considering just things like correlation functions of a scalar field in a theory of a single real scalar field. And last class we developed Feynman rules for phi cubed theory. So that was the theory where the Lagrangian was just given by the usual free Lagrangian plus an interaction term that was cubic in the field phi with a coefficient g that is some coupling constant. And we were imagining trying to compute things in a perturbation expansion where g is small. And we developed a diagrammatic technique, which I'm going to review for you right now, for computing these correlation functions order by order in this small coupling constant g. So in particular, what we saw was that this expectation value can be computed by taking the variational derivative of what we called the generating function, z, where z is a functional of some source j of x. So z is some function that depends on another function j of x that was defined formally as a path integral over all possible field configurations, weighted by the inclusion of an additional term, linear in phi, weighted by our source j of x. So just to summarize, z is a function that depends on an arbitrary source. To some extent, you can think of z as a function that captures how your quantum field theory will behave when you introduce some source. And if we vary z with respect to the source and then set the source equal to 0, then that computes for you some generating function. And we developed an algorithmic procedure which allows you to compute this generating function z simply where we sum overall diagrams of the value of that diagram, which we could call d, divided by some symmetry factor that we could call s of d. And the rule that we used was that the diagrams that contribute are built out of 3 ingredients. So they're built out of external vertices, which we denoted with some black dot here. So an external vertex, say, gives you an integral of the source j. We have propagators, which give you factors of the Feynman propagator connecting 2 points. And then we have interaction vertices, which give you factors of the coupling constant. So here I've written down the Feynman rules that would allow us to compute this generating function at all orders in J. But of course, to compute a particular correlation function, we only need to compute this generating function to order j to the n. So sometimes when you see people discuss Feynman rules, or position space Feynman rules as they are called, sometimes people don't actually even phrase it in terms of a computation of the partition function, because what we could do is we could rephrase the Feynman rules that I just wrote down for you as the statement that if we want to compute, say, this expectation value, phi of x1 up to phi of xn, we can just use the following algorithm. So really all I'm doing now is I'm imagining computing this partition function z to order j and to order n, and then taking n variational derivatives. So in particular, this correlation function, really I'm just rewriting what I just wrote down above, is going to be a sum over all diagrams which are computed using the rule that to each external vertex, or let me say that a different way, we introduce an external vertex. Sorry, my eraser on this pen is not working very well. So each external vertex is represented by a point, and we get one external vertex for each position, xi. So here, up above, I was representing by a solid dot an insertion of that source j. If you want to compute the expectation value of a bunch of phi's, what you would do is you would just introduce some external vertex. Say we have a dot for the external point x1, and say another dot if you have another external point x2. You connect these vertices with lines using an interaction vertex, which is your trivalent vertex, and each interaction vertex will introduce a factor of I times g, and then you write down the value of that diagram simply by using the rule that each line in the diagram gives you a propagator. So, for example, a line between points x and y gives you a propagator d of x minus y. And finally, you need to integrate over the location of all of the internal vertices. And as we discussed above, you need to weight each diagram by 1 over the symmetry factor, where the symmetry factor is the number of ways to permute this diagram holding the external vertices fixed. So this algorithm that I've just written down for computing these correlation functions is the same algorithm that we derived last class. I'm just sort of rewriting it down here in a slightly different form, where instead of writing everything in terms of these currents, I'm just explicitly saying, let's say, for example, that we wanted to compute a correlation function. So let's say, for example, we wanted to compute the expectation value of phi of x1 times phi of x2. So how would you go about computing that? Well, you would introduce an external vertex for your location x1 and an external vertex for your location x2, and then you would sum over all possible diagrams that you can construct using the rules that we just wrote down above. Okay. So for example, at 0th order in the coupling, there is only one possible diagram that you could write down, which is the diagram that I wrote down right here, where you have one external vertex at location x1, another external vertex at location x2, and a single line connecting them. You can actually pretty easily convince yourself that there are no possible diagrams you could write down at order g, okay, because every g introduces a trivalent vertex, and there's no way of connecting. There's no way of connecting all of the lines together to get something with only two external vertices at order g. But at order g squared, you'll get a contribution that looks like this. So here we have two internal points. I guess we could call them x and y if we wanted to. And then at order g squared, there are actually going to be two other contributions. So there'll be a contribution that looks like this. So there's x1, there's x2, there's another internal vertex there at x, and another internal vertex there at a point we could call y. And then finally, there'll be one more contribution that looks like this, where you have 2 points now, x and y. And then there'll be terms that are of order g to the fourth. Okay? It's pretty easy to see, you can check it for yourselves, that there aren't going to be any contributions at order g cubed. Again, because there's no way of connecting up three interaction vertices together to have only two external vertices. So I just want to work out this example very explicitly so that you can see what's going on here. So again, if you want to compute a two-point function to order g squared, you would just write down all possible diagrams that you can construct with two external vertices, one for each point, x1 and x2, connecting them together using this trivalent vertex. And then let's just go ahead as an exercise and just write down what the formula is for phi of x1 and phi of x2 computed to order g squared using this algorithm. So at leading order, you just have the propagator, the Feynman propagator, between d of x1 and x2. So just to keep life simple, I'll just call that d12, just so that my notation is a little simpler. So here, I'll use a notation where, say, dxy is equal to d of x minus y, and d12 is equal to d of x1 minus x2. So that's the first term. That's the term that you would get in free field theory. And then you would get terms of order g squared. So you get a factor of I times g for each coupling constant. So you'll get a minus g squared. And you have four diagrams, each of which has two interaction vertices whose locations need to be integrated over. And the three contributions that you get, well, from this top diagram up here, you'll get a propagator that goes from x1 to x, two propagators that go from x to y, and a propagator that goes from y to point x2. So that's that first diagram. The second diagram, this one over here, what do you get? You get a propagator that goes from point x1 to the point x, and then another propagator that goes from x to itself. And finally, for the third diagram, you get a propagator that goes from x1 to the internal vertex x, a propagator that goes from the two internal vertices to from the internal vertex x to the internal vertex y, and then a dyyy. plus contributions that are higher order in the coupling. And now the only thing left to do is to determine the symmetry factors. Yes, there's a question?
I think you're missing.
Oh, sorry. There's a D. Oh, sorry. Going a little fast there. dx2, and then here a D. Sorry, I was a little fast. There's, of course, a dyy and a dy2. Yeah, sorry about that. Just going a little fast there. Good. Okay, and so now we need to write down the symmetry factors. So what are the symmetry factors of this first diagram? Well, the only symmetry that we have is the one that interchanges these two propagators here. Okay. So the symmetry factor of that first diagram is 2. For the second diagram, we have 4 symmetries because you can interchange both of those propagators with one another, so you get a 1/4 here. And in this final diagram, you can interchange you can flip that propagator, so you get a 1/2. So, are there any questions on this computation? Yes. Good. Yeah, so the rule is simple. So the rule is, let's say that we wanted to compute, let's do a different one. Let's just write down the diagrams for a second. Let's say that you wanted to compute a 3-point function. What do? Well, you start by writing down 3 external points, x1, x2, and x3. And then you try and connect them up using some sort of diagram. So if we wanted to write that schematically, you might just write it like that, where I've written some blob here to represent any possible Feynman diagram that you could use to connect up those 3 external vertices. So for example, there'll be one term that looks like that, and then there'll be another term, say, that looks like that, and then there'll be 3 other terms that look like this, sort of very similar ones, where we have 2 vertices connected and a 3rd vertex disconnected. So that would be at order g. Then at order g squared, well, you'll get lots and lots of other sorts of different things. But, for example, one of the interesting diagrams, and one that we will spend some time looking at later on in this course, would be a diagram like that, which is order g cubed, and so on and so forth. So the idea is that you just write down your external vertices, one for each point, and you just connect them up. You write down all possible diagrams that would connect up those vertices using a single trivalent vertex, by which I mean a vertex like this, where 2 lines can come together and join to make a 3rd. Yeah?
We know the order of G by counting the number of times we see a vertex?
Exactly. Exactly. The number of vertices is the number of powers of G.
And when it's not connected,
We're going to spend a lot of class today talking about the not connected diagrams and concluding that we don't have to worry about them. So don't worry about them too much, but that is exactly the subject of today's lecture, why we actually don't have to worry about the connected ones. A priori, if you just use if you went through the derivation of the Feynman diagrams carefully that I gave you last class, they're going to be there. Okay. And the question is, what do we think about them and what do we do with them? So that's exactly where we're going today. Okay. Now we're going to conclude that we actually don't have to worry about them, but for reasons that are kind of interesting. That's something that we'll talk about today. There's a second question, of course, that you might worry about, which is that most of the symbols that I wrote down in this formula don't make any sense. For example, I'm computing here dyy, which is the propagator that connects point y to y. Okay. So that actually is infinity, right? Because remember that these propagators go like, say, for a massless field, 1 over x minus y squared, when x and y are very close to one another. And so that blows up as x approaches y. So what do we do with that divergence? And it turns out that the answer to what we do with that divergence is the same as the answer to why I don't care about the disconnected diagrams. So that's what we'll discuss today. Yes, question?
Just back a little bit, what do you mean when you say Feynman rules? Do you mean this prescription?
The Feynman rules are this prescription for computing the perturbative corrections to a correlation function using an expansion as a sum of diagrams. So here I've written down for you what are called the position space Feynman rules because I'm computing a correlation function. It turns out that there's a second kind of Feynman rules which are called the momentum space Feynman rules, which are actually much simpler. Those are what you would use for computing scattering amplitudes. Those are something that we'll just meet starting next class. But yes, so the Feynman rules are these rules for constructing a contribution to a correlation function as a sum over diagrams. In other words, the Feynman rules are the rules that say, if I hand you a diagram, what is the number associated with that diagram? And here's the number, right? You know, those diagrams are formulas, right? They're just ways of writing, a different notation for writing down a formula. Yes?
I just have a question about the symmetry factor.
Yes.
And that is,
Always confusing.
why
Yes.
why does a diagram that has a higher symmetry count for less in the Feynman integrals here?
Yeah.
Because to me, I mean, I feel like if there's more symmetry, then there's maybe more different ways that nature can let this happen. And intuitively, I would think that it would be the inverse for the symmetry factor that we attach.
Well, I mean, one just has to go through this derivation that I don't know if there's a particularly intuitive answer to that, except that, remember how we derived the Feynman diagrams by taking this generating function and expanding it order by order? Terms that have a lot of symmetry, we sort of wrote down in that expansion, we had a bunch of vertices and a bunch of ways of contracting up the vertices. And maybe the way that you could think about it is that if you write down a random diagram, it's going to have few symmetries. Okay? So finding a diagram with symmetries is a kind of quote-unquote rare thing that would happen when you start connecting up all of these vertices together. I don't know and so that might tell you why its coefficient is smaller. I don't know if I have any more intuitive way of explaining it to you. Except I could say that, if I wanted to, and I might have done this last year, but I think I'm going to spare you, I could ask you just to work out explicitly, did I make you guys do it last year? Yeah. Work out explicitly what the generating function is to some high order, start taking variational derivatives, and explicitly find all of the symmetry factors by hand. It's totally doable. I mean, it's just not fun. Yes, question?
I haven't been intuitive way of explaining it.
Okay.
Basically, last class, we went over all the combinatorics, right? We saw all the equivalent ways of putting down the diagram, and now you're just accounting for the ones that are actually the same diagram.
Yeah. That's right. That's right. It's just, so, I gave a derivation of it last class, but I don't think I have anything different to add that I didn't say last class. Yeah. Good. So for example, those of you who've started doing the problem set for this week, you're going to write down the Feynman rules for an integral, a one-dimensional integral. And in order to get the correct answer for that integral, you'll have to figure out various symmetry factors. And so in that case, you can work this all out in complete and gory detail. Okay. So hopefully the idea is clear that to compute the basic observable in quantum field theory, this correlation function, you just have one external vertex, one of these dots here, for each operator that you're computing a correlation function of. And this Feynman diagram expansion can be morally thought of. Each picture in this expansion sort of tells you a story about different trajectories that particles can take where they break apart into other particles and then reform again to compute, at the end of the day, the desired correlation function. And the sort of remarkable thing, and the thing that I really want to emphasize, is that the same procedure works for all sorts of interactions. So, in particular, so let's imagine that instead of a phi cubed interaction, we had a phi cubed interaction plus a phi to the fourth interaction. Then what rules would we use to calculate the perturbative contributions to some correlation function? Well, we would use the exact same rules that we wrote down above, except we need to add a new interaction vertex. Which, instead of being 3 vertices that come together at a point, you now have 4 vertices that come together. So, for example, if you have a process where 2 particles come in and scatter off of each other and 2 particles go out, that's the sort of thing that would be represented by one of these phi to the fourth vertices, or one of these quartic vertices. And it's important to note here that I chose this 1 over 4 factorial factor very carefully. Remember, the 1 over 3 factorial in front of the phi cubed interaction was what allowed me to have sort of a simple set of Feynman rules where all of the combinatorial factors were taken care of so that I would get a 1 here. Similarly, that 1 over 4 factorial there is necessary in order to have a coefficient of 1 here. Okay. You could, of course, remove that 4 factorial from the definition of lambda. Then you would have to put a 4 factorial back in the Feynman rules. And this does not just work for all sort of interactions, but also for theories with multiple fields. So, just for example, let's imagine that I have 2 different kinds of field. So we could call one a phi field and one a chi field. And let's say that our phi field has a mass, and we could also say give it some phi to the 4 potential. And you could also add, let's say just for fun, a coupling where a chi particle can turn into 2 phi particles, and we'll need to include a combinatorial factor associated with that. And then you could imagine adding all sorts of other Feynman diagrams. And then, in this case, you would have Feynman rules where instead of having just one type of particle that can propagate around in these diagrams, we have 2 kinds of particles. So in particular, we have 2 types of vertices. So you have an external vertex where you have a phi particle as well. So that's the vertex that you would use to represent some external particle phi inserted at a position x. And you would have a different type of external vertex that we could say denote with a wavy line instead of a straight line, where you would have your particle chi. You'll have 2 different types of propagators. So for example, you'll have this propagator here. This would be the phi propagator. And then you'll have your wavy line propagator, which would be your chi propagator. And you'll now have 3 different kinds, or sorry, two different kinds of vertices. So what sort of vertices do we have? Well, we have a phi to the fourth interaction term. So we have one vertex like that, each of which gives you a factor of the coupling constant lambda. And you'll have another interaction vertex where coming from, oops, sorry, I gave you a chi phi squared, not chi squared phi squared. That's what happens when I change my mind about what kind of interaction vertices to write down. But this will give you a factor of I times E, where E was the coupling constant was the name of the coupling constant that I gave to this interaction term. And of course, I could add all sorts of other different terms to this Lagrangian if I wanted to. I could add an m squared chi squared term if I wanted to. I could add a phi cubed term. I could add a chi squared phi squared, all of that sort of stuff. You know, I actually happen to write down this Lagrangian for you right here because it's almost exactly the same as the Lagrangian of quantum electrodynamics. If I called chi the photon and I called I called phi the electron field, then these are the exact sort of interactions that you would have in electromagnetism interacting with an electron. But of course, there are other sorts of theories that you could have. We would have other sorts of interactions. And so, for example, in this theory, if you wanted to compute, say, the two-point function of the chi particle, well, at leading order, you would just get that free propagator. And then your first correction would be something like that. That actually occurs in electromagnetism. It's an important correction. And then you would get higher order terms. Interestingly enough, so this term would be order E. This term would be order 1. And then it would be a straightforward exercise. You can do it for yourselves to go ahead and write down other sorts of diagrams that would contribute at higher order.
I think your second diagram was the wrong.
Oh, I'm sorry. That's because I changed my mind as to what I was going to compute. Sorry, that's because when I decided what I was going to use as an example, I changed my mind in real time during the class. Okay, so what sort of diagram do you have? You'll have this guy. Thank you. Good. Which is, of course, order E squared. Okay, much better. Interestingly enough, if we were talking about electromagnetism, that diagram that I've written down is very important. It's what describes the screening of electric charge in quantum mechanics. So in particular, if you have, well, I don't know how much we want to go into it, but it describes a quantum mechanical process where a photon breaks apart into an electron and a positron, and then they recombine again. There's all sorts of interesting physics associated with it, which we could go into. But for the time being, I'll just mention that it's a very interesting and important type of diagram. Yes, question?
Can you have an order E interaction?
Not in this theory that I wrote down. Not in this theory that I wrote down.
Sorry.
In the example that I wrote down in my notes before I changed my mind while giving the example, yeah. If you have an electron, you could never get an order E contribution to that diagram. Yes, good. Okay. I'll make one comment about these interaction terms. Which is that in order to make all of the combinatorial factors work out, usually what we're going to do is normalize our coupling constant so that, for example, if you had a phi to the 12th chi to the 127 interaction term, you would normalize that coupling constant by dividing by a 12 factorial and 127 factorial. It's all of the different permutations of the phi's and the chi's in that term that would leave that term invariant. And if you think about it, it's precisely that combinatorial factor that you would need in order to just have a 1 here. Okay, I don't want to go ahead and draw a diagram with 139 vertices coming in together. But it's the one that you would have if you, it's the combinatorial factor that you would need in order just to have a 1 there. Good. Okay, so in principle, at least, you could now take all of the theories that we've studied so far in this class and start writing down their Feynman rules. So for example, we introduced, on your last problem set, for example, you started writing down the various different types of interacting theories that would be relevant for scalar theories, theories with spinors in various dimensions, and you could just go ahead and start writing down their Feynman rules. Okay. There are a couple subtleties. So for example, when we have spinors, then you have to ask what do the spinor indices do when you have these Feynman diagrams. When you have vector particles, such as photons, you have to ask what does the vector index do when you write down these Feynman diagrams. There's a couple of little subtleties, but basically at this point you could go ahead and just start writing down these Feynman rules. And indeed that's what we're going to do. But before we do that today, I just thought I wanted to do a little bit more general sort of Feynman diagramology in order to simplify this discussion a little bit and to talk about those, those disconnected diagrams that we encountered above. Before I do so, I should pause and see if there are any questions. Even if the derivation of the Feynman diagram prescription that I gave over the last week is unclear, hopefully at least the end result, the algorithm that we're going to use, is clear. Are there any questions on that? Like if I told you to compute, say, in this theory up above, if I told you to compute the amplitude for, 2 chi's, a chi-chi, phi-phi correlation function, is there anyone who would have any problem writing down the diagrams order by order that would contribute to that? If there's anything unclear, go ahead and please do let me know. For example, there's one diagram that would, yeah, okay. Okay. So what I'd like to do now is just a little bit of, spend a little bit of time sort of thinking a bit more generally about the structure of the Feynman diagram expansion. So in particular, so far, what we've done is we've included not just connected diagrams, but also disconnected diagrams. But it turns out that if all we care about is computing correlation functions, it turns out that one can actually completely reduce the problem just to the consideration of connected diagrams. And this is a sort of beautiful kind of combinatorial argument. It's sort of a slick argument, so one has to sort of pay attention a little bit. But if you think about it, it's really quite beautiful. So what I want to do is I want to just think about the set of all connected diagrams rather than the set of all diagrams, period. So I'm going to denote by C sub I a connected diagram. Where I here is an index that labels all of the connected diagrams. And then I want to think about a general diagram, not just a connected one, as a product of a bunch of connected diagrams. Every general diagram can be written as a product of a bunch of connected diagrams. And what is the formula for a general diagram? Well, each diagram, so let's say that we have a general diagram where each connected diagram, C sub I, appears n sub I times. So if you have a general diagram, where the connected diagram C sub I appears some number of times, then the general formula for that diagram is just going to be Ci to the Ni power, and then you take the product over all possible connected diagrams. And of course, one has to divide by a symmetry factor. And in order to understand what that symmetry factor looks like, let's just imagine a particular example. Okay. So let's imagine that you have this connected diagram. And you want to write down, say, a general diagram where you have that connected diagram appearing twice. And if you want to make life more interesting, let's say that you have another connected diagram here that appears 3 times. Then, of course, you'll have symmetry factors of the individual connected diagrams, which are included in the number Ci. They're included in what I call Ci. But you'll also have an additional symmetry factor that occurs because you can permute those connected diagrams amongst one another, so that this extra symmetry factor Sd, what is that? That's the product over I of Ni factorial. Just because if you have a particular diagram appearing n times, there are n factorial different ways that you can permute those different connected diagrams amongst one another. Okay. So that means that a general diagram where you have the connected diagram Ci appearing Ni times is given by the product over I of 1 over Ni factorial times Ci to the Ni. Everyone with me so far? So let's now imagine computing the partition function, or the generating function. So the generating function is supposed to be the sum of all diagrams. And every diagram can be written as a product of connected diagrams. So that means that you need to sum over all possible values of those integers Ni of the value of the diagram where you have the connected diagram Ci appearing Ni times. So you have to sum over all collections of integers Ni, collections of positive integers Ni, 1 for each connected diagram, type of connected diagram, times the value of one of those particular diagrams. So if you just stare at that sum for a second, what we have is a sum over all possible collections of integers Ni times the product of over those integers I. And if you think about it for a second, what is this? This is just the product over all connected diagrams times the sum of Ni going from 0 to infinity of 1 over Ni factorial Ci to the Ni. What's that? Well, what is it? Well, that's a sum that you may recognize. It's the product over all connected diagrams of the exponential of the value of that connected diagram. And what is the product of a bunch of exponentials? It's the exponential of the sum. So the full partition function is the exponential of the sum over all connected diagrams of CI. I mean, it's worth staring at that statement for a second. The full partition function, z of j, is a sum of all diagrams, not just connected diagrams. But every diagram is a product of a bunch of connected diagrams. And there's a very simple way of restating the statement that every diagram is a product of connected diagrams. It's just the statement that you take the sum only over connected diagrams and you exponentiate it and you get all diagrams. That's kind of what the exponential does for a living. Okay. It takes some things, the exponential is precisely the function that does the combinatorics of turning connected diagrams into disconnected diagrams. Good. So, another way of saying that is that the log of the generating function is the thing where you only sum over the connected diagrams. Notice that the symmetry factors were crucial here. They gave you that 1 over n factorial to get something to sum up into an exponential. So, in fact, let's consider a simple example of this. And in fact, this is an example that we already did. It was the first example of a Feynman diagram that we did in this class. So let's consider a free theory. So this should be the exponential of the sum of all connected diagrams in a free theory. Well, in a free theory, there's only one possible connected diagram that you can write down. That's it. And if you remember in our computation of the free partition function, it was precisely just the integral d4x, integral d4y, j of x, delta of x minus y, j of y, with, of course, symmetry factor out front, because you can permute those two vertices. And so you can see here that indeed the free theory, our answer for the free theory is precisely just the exponential of a sum of a bunch of connected diagrams. So that, for example, if you were to expand this out, you would get 1 plus this diagram plus the square of the diagram, and so on and so forth. So is this clear? I mean, it's kind of a sort of amazing. I'm always sort of amazed by this combinatorics. But now we can take this one step further. So the generating function is the exponential of the sum of all connected diagrams. But let's imagine that we actually want to compute one of these correlation functions. So we have to take the derivative of z with respect to a bunch of j's. And then divide by z with j equals to 0. And what is z of 0? So z of 0, what is that? Well, that's just the exponential of the sum of all connected diagrams with no external sources. So we have a name for a connected diagram with no external source. We call those vacuum diagrams. So they would be, so for example, you would have something like, say, that, plus that, plus that, and so on and so forth, say in phi cubed theory. So the actual thing that you need to study when you compute a correlation function is z of j over z of 0. Okay? So what is that? That's the exponential of the sum of all connected diagrams divided out by the exponential of the sum of all vacuum diagrams, that is to say, all connected diagrams with no sources. And the ratio of two exponentials is the exponential of the difference. So that's the exponential of the sum of connected diagrams minus the sum of all of the vacuum diagrams. So that means that the partition function that we care about for the computation of correlation functions is the sum, the exponential of the sum of all connected diagrams without any of the vacuum diagrams, or usually people say without any bubbles. So that is to say without any vacuum diagrams. So that means that we never need to worry, at least if you're computing a correlation function, about any diagrams which are disconnected from all of the external sources. So, for example, we never need to, if, for example, we were computing our two-point function in phi cubed theory, we never need to include things like, say, that diagram. Because if you were to include that diagram, that will just drop out at the end of the day when you normalize the vacuum state appropriately. Remember that this 1 over z of 0 that appeared here, this appeared because in the path integral we had to ensure that the vacuum state was normalized. Okay. So this arose because we demanded that our vacuum state was normalized. Good. So we just got rid of an infinite number of possible Feynman diagrams that we had to worry about. You never have to worry about these vacuum diagrams. I'm about to get rid of another infinite class of diagrams, but before I do so, let me pause and see if there are any questions. Yes?
So just to make sure what you mean by vacuum diagrams, you mean any diagram which simply does not have a source?
Exactly.
So when you mean bubble diagrams, for example, the tadpole.
Yeah,
is
we're
the
going to,
tad-
the tadpole diagram is connected to a source. That's
Okay.
the one we're going to talk about.
So it's not a bubble diagram.
Yeah, it's not a bubble diagram. Sorry. I was mixing my metaphor here. So a bubble diagram is the same as a vacuum diagram. That's just, I don't know, people sometimes use just different words for the same thing. Synonym, I guess that's what it's called. Good. Any questions on that? It's a kind of, I just love this. I mean, yeah. This argument that any diagram is just, that the partition function is the exponential of the sum of connected diagrams. I don't know. I just can't get over it. It's great. Any questions on that? Yes.
Yes. Okay, so this partition function of j divided by partition function of 0 gives us this really nice fact that we don't have to include new vacuum diagrams.
Yes.
Right. I'm trying to see exactly where that comes into play. So if you have a correlation function, then that is the 1 over z naught times all of those
Yes. Yeah.
derivatives.
So that's this formula.
Right. But it's evaluated at j equals to 0. So I'm just trying to kind of more explicitly see how we get this z of j over z of 0.
Well, this really came because remember that, you know, this came, you know, remember that this is a path integral where you insert a bunch of observables. But if you do that, remember that you're not guaranteed to get, so what you want to demand is that if you didn't have any phi's inserted there, you would just get 1, right? Because this, I haven't written out the vacuum state explicitly here. If we didn't insert any phi's in there, you should just get 1.
So just got to normalization.
So you just need to normalize the vacuum. So it's just some overall normalization.
Yeah.
Good. Excellent question. Any other questions? Okay, I won't make any. I could make some comments about times that you do have to worry about this, but I'm not going to. Good. Okay. So we just managed to get rid of an infinite number of Feynman diagrams. Okay, that was good. Let's get rid of another infinite class of Feynman diagrams. So you've seen that the Feynman diagram expansion appears to contribute to one-point functions of the form expectation value of phi in the vacuum state. So for example, this in our phi cubed theory would get a contribution that looks like this. Which, if you were to write it out explicitly, what would that be? That would be I times g divided by 2 because of a symmetry factor, integral d4x, integral d4y, dxy, dyyy. So this has the unfortunate property of being both 0 and infinite, or non-zero and infinite. Okay. 0 and infinite would be a sort of neat trick. But it's both non-zero, which is kind of confusing, and infinite, which is even more confusing. So diagrams that contribute to the one-point function are known as tadpole diagrams. And appear slightly confusing for the following reason. So, when we defined interacting quantum field theory, remember we said, well, we could consider any potential that is an arbitrary function of phi, but we decided to shift our value of phi so that the potential was quadratic around phi equals to 0. In particular, we shifted phi to remove any terms in L which are quadratic in phi. And if you think about it, terms in the Lagrangian that are linear in phi are precisely terms that would give you a one-point function of this sort. So in particular, we can always shift phi by a constant to set this vacuum expectation value to be equal to 0. To say that maybe a little bit more precisely, one of the things that you should note is that if you think about this one-point function phi of x, so the expectation value of phi in vacuum, the first thing that you should note is that this is just a constant in space just by translation invariance. You know, if you wanted to say that a little bit more formally, you would say that there is a momentum operator P, which generates translations, so that phi of x is e to the I px times phi of 0 e to the minus I px. And then you would use the fact that the vacuum state is translation invariant. And then this would tell you that the value of phi, the expectation value of phi at any point, must just be some constant. So we could always just shift the value of phi in order to set the one-point function of phi to be equal to 0. The way that you should think about this is that you should think about what's happening is that classically we made the decision when we wrote down the classical potential to shift the value of phi so that v prime vanished, so that phi at phi equals 0 you had no quadratic terms in the action. But what you find is that once you start computing quantum corrections, once you start computing perturbative corrections, suddenly you get a quantum mechanical contribution to the vacuum expectation value of phi. And just as you removed the vacuum value of the value of phi in vacuum classically by shifting phi, you can remove its quantum contribution as well by shifting phi. So just to make this all a little bit more explicit, explicitly what I want you to imagine doing is if you start with a interacting theory, say our phi cubed theory, we could always add to the Lagrangian a linear term so that, for example, if we have say there's our action. Here, I guess I've integrated it by parts, so maybe I'll write it in the more traditional way. So if you have, say, your action with your phi cubed interaction term, you could always add a term linear in phi with a coefficient that I've called y here. And you could always consider that as your theory. And then you could demand that we choose the value of y such that the expectation value of phi in vacuum is equal to 0. So just to say that a slightly different way, let's imagine you had the theory with y is equal to 0. So let's imagine you didn't have that linear term for a second. If you shifted phi by a constant, what would happen? Well, that m squared phi squared term would go to m squared phi squared plus a term linear in phi plus a constant. And so the constant term never matters, but this linear term that we're writing down here would matter. And what we're going to do is just demand that the one-point function of phi vanishes in the vacuum. If you like, this is part of our definition of what we mean by the vacuum state. Or, to put it probably a better way, this is a part of our definition of what we mean by the field. Our field, you can always shift what you mean by the field. Just because you started out using one variable phi doesn't mean you couldn't use a different variable phi plus a constant later. So we're just going to choose our field variable to be shifted such that its expectation value in the vacuum is equal to 0. So what does that mean from a practical point of view? So that means that in the Feynman diagram expansion, we now have a new vertex coming from this new interaction term that is linear in phi. So what does this vertex look like? Well, it just describes a line that comes in and ends somewhere. Okay? So just to introduce some notation, I'll just put a little box at the place where the line ends. When we had a cubic interaction term, we had three lines that came in and ended at a point together. If you had a quartic interaction vertex, you would have 4 lines that come and end at a point together. Here we have something that's linear, so we have 1 line that comes and ends somewhere. And just so that you can see the point where it ends, I've labeled it by a little box. And so that contribution to the Feynman diagram will be equal to I times y. So that, for example, if you were to compute, say, the one-point function of phi, what contributions would you get to this? Well, so here you have your external point x, and you get one contribution at tree level, where it matches up with your y vertex. Then you get a contribution that's linear in G that looks like this. This is the contribution we wrote down above, plus higher order terms. So what is this? This is going to be I times y coming from that first term, plus the term that we wrote down above. So what is that? That's I times G over 2 times the integral of delta xy. So let's call that point y, if that point's x, times delta yy d4y, plus terms that are higher order in the coupling. And so you can see that you can just set that equals to 0 simply by taking y to be equal to minus g over 2 times the integral delta xy delta yy plus terms that are of higher order in G. So the procedure that I want you to imagine is that I want you to imagine that we have some theory and we want to introduce an interaction term. And then we need to introduce another coupling constant into theory. Okay? So this new coupling constant is sometimes called a counter term. And this counter term is not a physical coupling in the theory in the sense that it's not something that you measure. Instead, what we do is we just introduce it and we set it order by order in perturbation theory in order to enforce some physical condition. So one of the things that you see that happens here is that this counter term y, it precisely subtracts off this infinity that we were worrying about. So it cancels the divergence that appears in delta yy when you take the 2-point functions at the 2 points and set them equal to each other. And so it cures both of our problems. It cures the non-zero-ness of the 1-point function and also these confusing divergences. So, you know, what I've done here might appear to be completely ad hoc, okay? Because, you know, I haven't described the general principle that I'm using for writing down this counter term. It turns out that there is a very well-defined and deep theory that we use when we write down these counter terms, and we use them to subtract off divergences. This theory is known as the theory of renormalization. And what we're doing here is meeting, probably for the first time or maybe the second time, an example of an infinity in quantum field theory that's being removed by imposing some physical condition. So in particular, just as in the problem set, we saw that the divergence in vacuum energy is unobservable. So too is the divergence in the expectation value of a single field operator phi. And indeed, it's a general principle that divergences in quantum field theory always are unobservable and only ever occur at intermediate stages in calculations. And that's a really very deep subject, and it's something that we'll spend a lot more time talking about next semester. You know, this semester I decided I didn't want to get too bogged down in infinities and divergences and stuff like that. So we will, on occasion, encounter divergences, but from the most part this semester we'll just deal with them as they come up, and then next semester we'll return in more detail to consider sort of the more deep theory of renormalizability in quantum field theory. But just to summarize, the value of y is chosen precisely such that the 1-point function of phi is equal to 0. So that the sum, so here I guess I should really put the sum over all possible diagrams where you have some stuff connected to a single external vertex is equal to 0. Now, if you actually think about that, that really has a kind of amazing implication. In particular, what I want you to do is I want you to consider a diagram of the following form. So consider a diagram where you have a bunch of stuff connected to a bunch of other stuff. Okay. Right. So you have, on the one hand, here we have some other stuff that has external vertices. And here you have no external vertices. But the value of y is precisely chosen so that when you sum over all possible diagrams, you get precisely 0. So in particular, for example, let's say that we had one contribution that looks like this. So you got some crazy diagram. Okay, there's some diagram. Okay. And then you have some counter term. And the value of the counter term is chosen precisely to cancel that crazy diagram. So just to say that in words, y is chosen so that any diagram with the property that if we cut one line, the diagram falls into two pieces, or divides into two pieces, one of which has no external sources, then that diagram vanishes. So another way of saying that is that the generating function, so we decided that this was the exponential of the sum of all connected diagrams with no bubbles, but it's also the sum of all connected diagrams with no bubbles and also no tadpoles. So, for example, yes, question?
Just a clarification. Is it both pieces vanish, or only the piece without?
Well, the total
diagram.
The total diagram vanishes, right? Because, let's imagine, so for example, this diagram here, so this diagram here, so this crazy diagram here, let's see if I can draw it again. This diagram here, it contributes to the one-point function of the phi in vacuum. And so that means that when you compute the one-point function, you have to add some value, some term to y to cancel the contribution of that crazy diagram. And so that means that not only does the value of y cancel that crazy diagram in the one-point function, it cancels it in every other possible diagram. So for example, let's say that you wanted to compute, say, the two-point function. So earlier we wrote down a bunch of terms that contribute to the two-point function. So we had a term like this. And then in a phi cubed theory, you would have a term like this, right? But there will also be a term like that with a counter term. And these two terms sum up to 0. So you can just forget about that tadpole diagram. So these two terms cancel. Which is good because this diagram was infinity. I don't know, did we actually compute it up above? We actually wrote it down, I think, up above. Did we write it down? I'm not sure if it was one of the ones that we wrote down. There it is. So there's this diagram here, and that diagram cancels. That diagram does not contribute. Similarly to these diagrams here. So in fact, when computing the two-point function, the only diagram that you ever need to worry about is that diagram. Good. Any questions on that? Okay, so we've done a yeoman's work today, right? We've gotten rid of all of the bubble diagrams, all of the tadpole diagrams. If we kept at this pace, there would be no diagrams left by the end of the week. Unfortunately, this is the extent of the sort of very general magical theorems that we can write down where we eliminate diagrams. What we're going to have to start with soon is actually doing the hard work of computing some of the diagrams that don't vanish. But that's for another day. Maybe before I end here, I should just pause and see if there are any questions. No questions? Yeah. Good. Okay, I will see you on Thursday.